Cool. Hey, everybody. So today we're doing topic 12, which is statistical distributions. But before that, I did want to talk about a couple things. So first, blog posts. So I didn't talk about this previously because I don't want y'all to have too many things going on all at once. But from phases 1 through 4, you have to write a blog post for each. And you basically just need 4 blog posts to graduate. Now, the way I'm going to do it is I would like your blog post to just be done before we start the next project. So anytime within the next 2-3 weeks, write up a blog post. This blog post can be on anything you want, and you gotta basically submit it here. So I will be checking blog post submissions right before we kick off the next project. I'll put a note in the homeroom, like an exact date that I'm looking for, but just within the next couple of weeks. And the way you submit it is also through Canvas. Now, on the lines of blogging, I haven't talked too much about this yet, but I highly recommend creating your blog on medium.com. Reason for that being, there's already a lot of data science content on Medium. There's actually a lot of Flatiron blogs already on Medium, and it's just a good way for people to find you. Medium also has really, really good search engine optimization. So actually, if you were to Google, I think if you Google me, Medium is one of the first things of mine that comes up. So I highly recommend that you write your blogs on Medium. If you want to find me on Medium, or if you want to find some examples of blogs, you can find me on Medium if you just look up my name. And also, I think I linked it to the bottom of the phase 1 project guidelines, which, by the way, for guidelines, if you ever wanted to look for those, they're in the resources Google Drive under phase 1. And if you go into the guidelines here, you'll find my Medium page right at the bottom here. Now, I linked my following because everyone I'm following, I think 95% of everyone I'm following is a Flatiron student. So if you just want to get, some inspiration for blog topics, feel free to click through all of these folks here. If you just want to read some examples of Flatiron blogs. Again, I think in terms of requirements for blogs, it does say, I think 800 to 1,000 words. I'm okay if you write just more than 500 words. And the topic can be about anything related to data science. It doesn't necessarily have to be very technical either. It can be just related to data science. I will say that most students end up writing their blogs about the project that they just did. So that's an easy option for you to go with if you want to do that. But yeah, feel free to click through all these different blogs to figure out what you want to do. You don't have to pay for Medium. If you do, I think Medium's membership, there are a bunch of paid articles. So if you want to read a bunch of paid articles, then yeah, you have to pay for a Medium membership. But to publish your own work and also to get paid for publishing your work, you don't have to have an account that you pay for. I personally pay for it because Medium is one of the main things I read, like highly recommend towards data science, actually. A lot of great data science articles for those of you who enjoy consuming this kind of info. So yeah, you got to do your blog just before the next project is, I would say before we start the next project. So maybe within the next 2, maybe 3 weeks, highly recommend just get a blog out there. Any questions regarding that, feel free to let me know. Does anyone have any questions at this point about blogs? Okay. The other thing I wanted to talk about was working on your phase 1 project. So almost all of you are done with your phase 1 project. I think pretty much everyone has scheduled their review, and we'll be done with our reviews by early next week, I believe. So congratulations on that. Everyone is on track to pass. And in case you want to work on your blog, on your project, let me just show you all an example. Let's see, let's just say, let's just see what's on my, let's just see what's on my GitHub first. Very likely, if you are working on your project now with your partner or with your group of 3, you're working on it together. Very, very likely when you're cleaning up your products, making them ready for use on your portfolio or just for putting on your resume, you probably want to clean up in your own way, which is perfectly fine. Just want to let y'all know that in order to do that without messing up each other's copies is to create a fork version of your project. So make sure you communicate with your project partner, and whoever's account the repo was initially created on, So for example, this was actually my phase 2 project from like 2 years ago, as you can see. This is not created on my account, but for me to make my own changes, and for example, like I just wanted to clean this up. I think that's what I did. I don't remember, but I just forked my own copy of it. Okay, I guess I didn't clean it up, but anyways, I forked my own copy of it. So any changes that I make to this over here will not affect my teammates' version, because after graduation, I kind of wanted to do my own thing with all of my projects. So that's something that you can do with your project if you intend on making changes to fit your own, maybe your own voice, your own method of analysis, so on and so forth. So in case you want to do that, just fork your own copy, and it will not affect other people's versions of this. So make sure you communicate, especially if you are the owner of the repo. If you want to make changes, make sure you're communicating with your project partner. All right, any questions about this before I get into material? Cool. All right, in summary, blog, try and get one done within the next couple of weeks. And then for your projects, this project and future projects that you work on with other people, you can fork a copy after you're done in order to keep making changes independently. Okay, let's get into statistical distributions. These slides, and I believe the slides for tomorrow they're also already up on the repo. Okay, let's just throw up this presenter view. Okay, so yesterday we talked about probability. Today we talk about statistics. And statistics is kind of a branch off of probability. And starting today, we'll start to see things that are going to be more directly related to what we're going to talk about with regards to our machine learning modeling later at the end of this phase. So what are we going to hit on today? Expected value and variance, PMF, PDF, CDF. I'll explain what those are later. Bernoulli and binomial distributions, normal distributions, and a one sample z-test. We're just going to set that up for now. The main things to take away from this slideshow, I would say just know how to read a PDF, and I'll get into that in a little bit. And also normal distributions. Those are going to be the most important things. But I'm going to talk about these things in this slide today, in this slideshow today. Okay, expected value and variance. So for any random value or any random variable, there is actually an expected value and a variance. Using an easy example, let's talk about dice roll. An expected value, you can sort of think of a weighted average of what you expect your value to be. So with an example of a dice roll where your possible values are 1, 2, 3, 4, 5, 6, and the probability of getting each is equal, the expected value would be the average of them all. So it would actually be 1/6 times 1 plus 2 plus 3 all the way plus 6. And that actually gives you 3.5. I'll break down this equation. So this equation is a very, very general form equation of what I just did. So if we talk about a dice roll, this is the probability of that result, and this is the result itself. So this just means we're summing it up. So for a dice roll, we're going to take the sum, and I've gotten really good at like writing with my mouse since I started teaching. But anyways, we're going to take the sum of the probability of something occurring, which is for a dice roll 1/6, multiply by its value. So this is just for 1. We're going to do the same thing, 1/6 times 2 plus this, add, so on and so forth to 1/6 times 6. So we're going to sum all of this up, and this should give you 3.5. If the dice was a weighted die, so let's say its probability of rolling a 6 was much higher than normal, and then as a trade-off, maybe the probability of getting a 1 or a 2 is much less. You just have to reweight these, and then your expected value will actually change with those new probabilities. So expected value is sort of like a weighted average value that you would get out of your probability. If we want to do another example, let's talk really quickly about flipping a coin. And so let's just assign tails to be 0 and then heads to be 1. So the way that we get the expected value for a coin flip, for a fair coin, we know that each value has a probability of 1/2 occurring. So we just have to add these together. Oops, what I'm here. So 1/2 times 0 plus 1/2 times 1. The expected value is a half. So that's kind of expected value. If the coin was weighted, if there's a higher chance of getting a heads using this coin, the expected value you would expect to be higher than 0.5. Now for variance, this is just the average deviation from the mean squared. So variance is actually standard deviation squared. We'll talk about standard deviation in a little bit, but just to break down what this formula is, we're not going to work the whole thing out, but for every value, we have this same probability, the probability of it occurring, and then you also have the value itself minus the expected value squared. So in the case of a dice roll, I'm not going to work this whole thing out because in your labs that actually walks you through that process. We actually will calculate the expected value first, get a 3.5 over here, and then for our values 1 through 6, we'll sub in here. Here our probabilities of 1, 6 will be in here. I forget what this works out to. I think it's like 0.1 something. I'm not going to guess. But basically that will give you our variance. For specific name distributions, and we're going to talk about a few today, there are often formulas for the expected value and variance. So let's just say we have the probability of, I don't know, the probability of, oh, we're going to talk about this in a little bit. Let's say you're shooting basketballs and you're making 10 shots and you want to find the probability of making 1 out of 10, 2 out of 10, 3 out of 10. And the probability of making a single shot is like maybe 0.2, for example. You can actually find the expected value and variance for that distribution too. And that's actually an example we're going to talk about later. And instead of working out this entire formula for that, for some named distributions, there are more straightforward formulas to get the expected value and variance. Okay, we're going to talk in more detail about this with regards to our specific random variables later. Okay. Next up is a probability mass function. Before I get into this, there is a probability mass function and there is a probability density function. Now they both essentially give you the same information. The only distinction between the two is a probability mass function gives you probabilities for discrete random variables, meaning any random variable that gives you a discrete result. For example, a dice roll can only give you 1, 2, 3, 4, 5, 6. Coin flip can only give you heads or tails. Whereas in a probability density function, and we'll talk more in detail about this later, it's for continuous variables. To be honest, most of the time we will actually be working with continuous variables, but just good to know. But an example of a continuous variable is probability of temperatures, where your temperature can actually fall between a range of values. So that's a distinction between discrete and continuous variables. So the differences between probability mass function and probability density function is mass is for discrete, density is for continuous. So probability mass function, the information shown will actually apply directly to probability density function, but it's easier to explain it in this context first. So a probability mass function basically associates probabilities with discrete random variables. And discrete basically means that there's a known number of possible outcomes. And so this example over here is just saying that, okay, possible values are 1, 2, 3, 4, 5. And the associated probabilities with each of these are, I guess, 0.31 for 1 and 2, about 0.15 for 3, 0.08 for 4, and 0.15 for 5. So the thing about a probability mass function is that the sum of all of these bars has to sum up to 1 based on our probability axioms that we had talked about yesterday. So given some probability mass function, if you're asked to find what the probability of getting something is, you can actually read it directly from here. So an example would be, okay, what's the probability from this random thing? What's the probability of getting a 4 or a 5? You would just say, okay, probability of getting a 4 or 5, this is 0.08, this is 0.15, the probability would be 0.23. So that's how you can read something like this. If we're talking about our usual dice roll example, our dice roll example 1 through 6, that means the probability of getting each is 1/6, which I believe is 0.0167, I think. So if you had a PDF of a dice roll, let's just draw this out super quick. If I had a PDF of a dice roll over here, And I'm going to just draw this with a bunch of lines. This is the probability here. We have 1 here, and then we have, I'm going to try and draw 6. Okay, there we go. We have 6 there. And then what the PDF will look like, it's not going to look pretty, but you'll have it basically be like 6 straight bars across for 1, 2, 3, 4, 5, 6. Okay, let's just imagine this is the same. 4, 5, 6. And then the value over here will be 1, 6. So the same rules follow. The sum of all of these boxes will add up to 1. And you can immediately read, okay, what's the probability of getting a number from 1 to 3? You would just add 1, 6 plus 1, 6 plus 1, 6. That's something that you can read off of a probability mass function. Questions about this? Okay, so let's move on to a probability density function, which essentially tells you the same thing. It tells you the associated probabilities for specific values. Again, on the y-axis, it is the probability. On the x-axis, it's your value. So in this example, we're looking at the temperature on June 1st in New York City. And this is just like the probability of what they said the temperature will be on June 1st. And because there is no known number of possible outcomes, technically the number of possible outcomes here is kind of infinite, because you can have like 80, you can have 85, 90, but you can also have like 81, you can have 80.5, 80.25, you can have as big or small number of like increments as you want. So therefore this is a continuous random variable. In kind of a similar vein, whereas all of these bars had to add up to 1, if you're familiar with calculus, and okay if you're not, the whole idea here is that instead of a bunch of boxes like a bar graph or a histogram, a PDF is usually some sort of smooth curve. And therefore we can't really like add up the boxes underneath. You can definitely estimate that by drawing boxes underneath a curve. I think they did that in high school math. I also forget. But the idea here is instead of boxes adding up to 1, it's the entire area under this curve should add up to 1. So the entire shaded area over here under this blue curve, I'm going to draw this here, should add up to 1. So a way to approximate that, might have seen this in math class like long time ago or not, I don't know. But if you were to estimate with rectangles under this, these rectangles should add up to about 1. Because rectangles have some sort of width versus like a singular value, these rectangles will help you estimate ranges for probability for ranges. So in this estimation example, they drew this middle box over here that is, I guess, roughly 79.3 to, what did I just do? 79.3 to 80.8. They basically measured the height of this box here, which is roughly, I guess, 13%. So that's one way of reading a probability density function. Probability density functions, out of all of these functions that we're going to talk about at the start of this slideshow, reading probability density functions is going to be the most important one. So always remember that the y-axis is the probability associated with the value, and the values are going to be on the x-axis. Any questions at this point? All right. Okay. So next, this one's a little bit less often used, but good to know that it exists because you can actually do this in using SciPy, using Python. There's also a cumulative distribution function, which actually applies to both discrete and continuous variables. To be honest, I've also come across the term cumulative mass function in some textbooks, which would be the difference between a discrete and a continuous distribution function. But in this case, in our curriculum, they call cumulative distribution functions the same thing for both discrete and continuous. And as the name suggests, it shows you the cumulative probability. So for example, with the dice roll here, you can see that at every value of 1, 2, 3, 4, 5, 6, it kind of has like a stepwise looking function because every time you increment it, there's no in between a 1 and 2. So therefore the cumulative value just jumps. So in this case, you would ask, okay, what is the probability of rolling a number up to 4? So probability up to 4, you read at the top of the step. So probability of up to 4 is roughly, I think this is roughly 0.67. So that is the cumulative probability. In this case, on the right-hand side, we have the cumulative version of what we saw earlier. So the cumulative version of this, and it basically, a use case of this is like, okay, what's the probability that the temperature will fall below 85? So probability of temperature falls below 85 as an example. You'll basically trace up here and then look across here. Okay, probability of the temperature being below 85 is going to be roughly, I don't know, this is like maybe 0.95 or so. Important things to know about CDF, a CDF always starts at 0 and ends at 1. The curve or line or step or whatever always starts at 0, ends at 1 because it's cumulative. And yeah, if anyone is interested in like more of the math that goes behind this, if you take the derivative of this or of this, it'll actually give you your PDFs and PMFs. So if you take the derivative of this temperature graph, it will actually give you this graph over here. And if you took the derivative of this, it'll give you the dice roll that was straight across. Not super important to know, but just in case anyone was curious. Questions about this? These are just graphical representations of probabilities. And the most important one to remember, to be honest, is really this one, the probability density function, because we'll be seeing quite a good bit of these. Questions? All right. Okay, so next we're going to talk about a couple named distributions. These are important to know just in case you're presented with a very specific scenario. You'll be able to quickly find out how to calculate these probabilities. So I'm going to talk about two today, the Bernoulli distribution followed by the binomial distribution. These are important because if you were trying to figure out how to calculate this in a quick way, you would know what to look up on Google to do it in Python. But anyways, to start with the Bernoulli distribution. A Bernoulli distribution is characterized as a one-trial binary outcome experiment. So a one-trial binary outcome experiment, you can think of it as flipping a coin. They're binary outcome. That means there's only two possible outcomes, heads or tails. A very common one would be like hit or miss. So maybe you are, again, throwing basketballs. You successfully make a basket 0.2 of the time, you miss it 0.8. That's also a binary outcome. And important thing to note here, it is a one trial experiment. So every time you do the action or conduct the coin flip or throw the basketball or do the experiment, you restart as a one trial. So in this example, let me just highlight a couple things on this slide here. We have this first line here of like x squiggly line ber p equals to 0.8. So that's a mathematical way of characterizing a Bernoulli distribution. So this is just saying that x is a random variable. This tilde squiggly line is just saying that x is a random variable. It is Bernoulli. BER is just, I guess, mathematically known to be short for Bernoulli. And the p, the probability of success, in this case is 0.8. So here, because it is a binary outcome, you really only need to know one of the probabilities to know the probability of the other outcome. So in this case, they usually say the probability of success is p, which is equal, in this case, 0.8. So these are the PDFs and CDFs of a Bernoulli experiment with probability of 0.8. You can see here you have two outcomes, 0 and 1 for your PMF, and for your CDF as well, 0 and 1. Here you can see the probability of getting a 0 is 0.2, probability of getting a 1 is 0.8. And your CDF, because it's cumulative, your 1 pretty much is always just a bar that goes straight up to 1. But for 0, it's the same, it goes to 0.2. Now, expected value and variance. There are formulas that I actually have written down. I'll show you all where that is in a little bit. But the formulas for calculating expected value and variance for a Bernoulli experiment, expected value is always p. Because if you were to work out these probabilities, because it'll be 0 times probability of 0, 1 times probability of 1, the expected value always is equal to p. Now the variance, and this you can actually do by working out the formula, but the variance, a quick formula for that is P, oops, what am I doing there? It's P multiplied by 1 minus P. So in this case, we have 0.16 because P is 0.8, and then 1 minus P is 0.2, and that actually gives you 0.16. Questions about this? All right, I just wanted to show you all where you can find this information. If you go into the Flatiron resources and you go into phase 2, you'll actually see a, well, actually, I don't have that there. I'm going to add it there in a little bit. But here you can see, we're going to talk about some of these over the next week. I have basically a summary thing of information. I have a PDF of this expected value variance thing, and I'm going to add it in there later today. I didn't realize it wasn't in there. But anyways, not super important to remember, to be honest, but just know that for some named distributions, you can find formulas that are easier than the formulas that we talked about before, easier than these formulas to figure out the expected value and variance for some distribution. So this is a Bernoulli distribution. Any questions about this? Sweet, pretty straightforward. Just think of a 1 trial, 2 outcome experiment. Next, we're going to talk about the binomial distribution, which is actually my favorite distribution. It is a multi-trial binary outcome experiment. So a way of thinking about this is, let's just say, the only example I can think of is basketball right now. But let's say you're shooting a basketball and you have a 0.8 chance of getting the basket each time. What is the probability that you get X shots out of 3? This would be this experiment here. So a binomial random variable is characterized by 2 things. So previously we had the Bernoulli only being characterized by 1 thing, the probability of success. With a binomial experiment, we have 2 parameters that define what the distribution is. First of all, similar to earlier, we have the probability of success, which in this case, let's just keep it at 0.8. But also we have the number of trials. So the number of trials is also part of the calculation of probability. So with this example of you're shooting the basketball 3 times, the probability of making the basket each time is 0.8. What is the probability that you get 0 out of 8? 0 out of 3, 1 out of 3, 2 out of 3, and 3 out of 3. That's what these probabilities are in the PMF and CDF. So here I actually put the formula for calculating this. This over here is actually the combinations formula, if you remember that from yesterday. So this is just another way of writing, let me just write it out just so that it's on the screen. This is another way of writing n factorial divided by k factorial times n minus k factorial. Again, this is not important to be memorized. I only have it in my head because I had to for my pre-Flatiron life. But this is basically that. And then you can plug in P, 1 minus P. Here in this case, K is the number of successes that you want to find the probability for. So let's say if I wanted to find, okay, you're making 3 shots. What's the probability that you make 2 out of 3? K is equal to 2 in this scenario. So here will be 2. Here will be n minus k, which is 1. And it kind of makes sense here. If you plug in the probability of making 2 out of 3, you would actually take the probability of success, which is 0.8. Take the square of that because 2 successes and then 1 failure, which is 0.2 over here to the power of 1 because 1 failure. And this is the number of ways that you can get 2 successes and 1 failure. If all of that just went over your head, that's absolutely fine. It doesn't matter so much for this for our use cases, but kind of good to know, I guess. So if you work this out for k equals 0, 1, 2, 3, it gives you this PMF over here. And of course, the CDF, same thing. If you just pretty much like stack the boxes on top of each other, you'll get your CDF. And you can see, as with all CDFs, it always ends at 1. Now for expected value and variance, these are the expected values and variances for this specific problem of you're making 3 basketball shots and your probability of making the basket is 0.8. Expected value and variance for binomial distribution, for expected value, it's actually n times p. So here n is 3, p is 0.8, 3 times 0.8 is 2.4. The variance is n times p times 1 minus p. That's how we get 0.48. We get 3 times 0.8 times 0.2. Again, not important to remember these formulas. I'll shoot up like a PDF summary of all of these. The most important thing to get away from here is if you are presented with this kind of scenario of like, what are the probabilities of having 9 successful baskets out of 12, maybe, you would use this to calculate that. Not so important to remember the formulas because that's always something that you can look up. All right, any questions regarding this stuff? Okay, next up, let's talk about the normal distribution. There's a lot of information on this slide, but these are all basically characteristics of a normal distribution. So normal distribution looks like this, and it's also known as a Gaussian or the bell curve. So if you've seen like the bell curve or anything that looks similar to this, you would say it resembles a normal distribution. And a lot of things that we're going to talk about towards the end of this phase are assuming some sort of normal distribution. So whenever you're doing your EDA or if you're doing some graphing or exploration of your data, if you see that your data kind of looks like this shape, you would then say it resembles a normal distribution. Let's first talk about what things would characterize a normal distribution. Okay, so let's go through these points one by one. So first, normal distributions are symmetric around their mean. So as you can see with this curve, it's pretty symmetric. It's symmetric about around whatever the average value is, which is, I guess, this mu over here. In a normal distribution, the mean, median, and mode are equal. That's actually something that's really interesting. I think in some of your phase 1 projects, a few of you have explored like the relationship between mean and median. And usually when your mean and median are different, it's slightly skewed. So that already in itself throws off the symmetry. So with mean, median, and mode being equal, that is another characteristic of your normal distribution. In real life, that's very rarely exactly the case. So as long as your mean, median, and mode are roughly equal, and what roughly equal means does depend on your context, you can say that it kind of resembles a normal distribution as well. The normal distribution here is actually a PDF. It is actually a different PDF, but similar to what we've seen with here, you actually read probabilities off of a normal distribution. So therefore, the area under this bell curve is equal to 1, just like any other PDF. Some other things, they are denser in the center and less dense in the tails. Of course, your extreme values are less likely, and your more average values or values around the average are going to be more likely. And then your normal distributions are defined by 2 parameters, the mean and the standard deviation. So mean and standard deviation are basically like what we talked about before. We had our expected value, that's usually the mean, and standard deviation is basically the square root of our variance. Not important to remember this, but good to know that any normal distribution can be characterized by different means and different standard deviations. In the next slide, we're going to explore some more of that. Very useful things to not fully memorize, but to be aware of are these statistics over here. Around 68% of the area of a normal distribution is within 1 standard deviation of the mean. So let's attach some numbers to this to make it a little bit easier to contextualize what we're talking about. So let's just say that this is, let's just say these are, I don't know, IQ scores of the general population. And let's just say that the average IQ score for the whole world is 100. I am making up these values. I don't know IQ scores, but let's just say the mean IQ of the world is 100. And the standard deviation, maybe through some like estimation or calculation, is, let's just say it is 20. Let's go with that. So with a mean of 100 and a standard deviation of 20, what does it mean when it says 68% of the area of a normal distribution is within 1 standard deviation of the mean? So standard deviation is 20. 1 standard deviation of the mean is basically 100 plus minus 20. So these would be the points 80 and 120. And for a normal distribution, roughly 68% of the area under this curve falls between these values. So that just means that the probability of someone's IQ being between 80 and 120 with a standard deviation of 20 is 0.68. So that's something that's just kind of useful to remember. You can expand this to standard deviations. 2 standard deviations would be between the numbers 60, 140, and the associated percentage is actually 95%. So that's just saying that what's the probability of your IQ being between 60 and 140? 95%. And then even more, we can go 3 standard deviations, which would be 40 and 160. So 99.7 of the data, 99.7% of the data will be between 40 and 160. So if you're asking what's the probability that someone's IQ is going to be between 40 and 160, almost 100%, which makes sense because the range is going to be pretty big, especially with this context. Something else I wanted to mention. Oh, yes. So this is actually a pretty useful tool to figure out what your outliers are. A very, very common practice, not common practice, but one common technique of removing outliers in your data or possible incorrect values is by looking at how far away from your mean with the context of knowing your standard deviation is a value. So let's say we're looking at IQs and we get an IQ value of like 250. Now 250, the probability of your IQ being 250, given these parameters of the mean is 100 and standard deviation is 20, the probability of your IQ being 250 is going to be very, very slim, very, very small. So if you got data like that, you might have reason to drop that 250 number. Similar for the other way, right? Like if someone tests with an IQ of like 5, very, very improbable for that to happen. So that's how you characterize normal distribution. And in thinking about that, also how you use standard deviation and your mean in contextualizing your values. Questions about this? Sweet. All right. So the next slide, we'll take a look at what different normal distributions can look like. So on this graph, these 4 curves are all normal distributions with different means and different standard deviations. So here you can see that the blue, green, and red all have a mean of 0. So you see that they're centered around 0. The yellow one just has a mean of 2. And they also have different standard deviations. You can see that the flatter one, this red one over here, has a standard deviation of 3. So that means 68% of the red curve's values fall between +3 and -3. So this area under here will be 68%. Now, similarly, in a different context, if we take a look at the green curve, the green curve here has a standard deviation of 0.4, which is much smaller than 3 in this context. So 0.4, I'm going to estimate it to be roughly here and here. So with this, you can see that it's a lot taller, and it makes sense that within one standard deviation, with the peak being much higher here, this area is not drawn to scale, but this area should be the same area as that red shaded area, because this is also within one standard deviation in the green lines context. So this green area is also 0.68. And you can do the same thing for the blue curve and the yellow curve. So that goes to show that it's very important to not only know the mean of a distribution, but also the standard deviation, because it does help you contextualize how far away your values should be. This is the expected value and variance, which you are usually given for a normal distribution. And in terms of the PDF and the CDF of a normal distribution, you do not have to memorize these formulas. In case you're curious, this is how you can plot one on a graph. I do not remember these formulas at all, but just in case you're curious, these are defined, just so that you don't have to do that like summation of whatever. Actually, if you want to do this mathematically, you would have to do a bit of calculus, integration, not important for data science at all. But this is just good to know that normal distributions can look very different with different parameters. Yeah, questions about this? These are all normal distributions. Okay. So let's next talk about the standard normal distribution. So the standard normal distribution is a particular normal distribution with an expected value of 0 and a variance of 1. And so this is called the standard normal distribution. And we'll talk about, I'll give you all like a scenario where this is going to be useful later. But this basically allows us to compare the values in different normal distributions by using something called z-scores. So a z-score basically tells you how many standard deviations away from the mean a single point is. And I'll set up a whole problem in a little bit, but this, just so you know, this is the formula for calculating a z-score. If you know the mean and standard deviation of a distribution for any value here, oops, what did I do here? I wanted to draw this. Okay, for any value x, so let's just say we're looking at this value of 70. This value of 70 over here, we can just take 70 minus the mean, which is 50, divided by the standard deviation. I actually don't know the standard deviation for this particular graph, but we can just say that, let's say the standard deviation is 10. If we say that the standard deviation is 10, and I think it is actually 10 now that I say it. Hold on, let me just get the correct color pen out. Okay, so it would be 70 minus 50 divided by 10, which gives us a z-score for this point of 2. So this has basically done a transformation of your value of 70 over here into 2 over here. And that's how we get from 70 to 2. So why is it important to know that the z-score for 70 in this distribution is 2? Let's go back to the last slide because I want to use the last slide as an example. So let's just say you have different classes of students and they all took a test. And let's say you just want to, I don't know, test the effectiveness of different teaching methods maybe. And so let's just use the yellow curve and the blue curve. So let's just say the yellow curve is class A, the blue curve is class B. And in both classes, there is a student that gets, and let's say these scores can range from -6 to +6. And in both of these classes, there is a student that gets a score of, let's use the example of 3. Okay, so I'm gonna use, oh, that's too close to yellow. Let me pick a different color. Okay, let's just say that in each class, there's a student that gets a 3. We wanna see how well this student, each of the students that got 3s in each class, how well did student A and student B do in the context of the rest of their class? So that's going to be our problem setup. So if we take a look at this score of 3 in the yellow class, you can see that, okay, the score of 3 in the yellow class did a little bit better than average since it's around here and the yellow curve is around there. The probability of someone getting higher than a 3 in that class is roughly this area. Oops, is roughly this area over here. So seems like that guy did pretty good. Now, if we compare to the blue class, which is this curve over here, the probability of someone getting higher than 3 is actually even smaller over here. So that kind of gives us a hint that if you got the score of 3 in the blue class, you actually did really, really good in the context of your class versus getting a 3 in the yellow, which is good, but not, I guess, as extremely good as you doing that in the blue class. If you want to compare that, let's say someone in this red class got a 3 as well. The probability of someone doing better than that would be this area over here. So for each of these curves, we can actually calculate a z-score for a person scoring 3 in each class. So let's start with the yellow one first. So for this yellow class, you see that the mean here is 2, standard deviation is 0.5. Let's figure out the yellow z-score. The yellow z-score, again, we want to take the value, which is 3 minus mu divided by the standard deviation. And this actually gives you a z-score of 2. Next, let's do it for the blue class. So for the blue class, we have z equals to 3 minus, in this case, the mean is 0, divided by standard deviation of 1. Z-score is 3. Cool. Let's just do for the red class, just because we have that there. For the red class, z would be 3 minus 0. And here, the standard deviation is 3. So your z-score is 1. So this basically gives us more of an apples to apples comparison of how a student getting 3 did with respect to each of their classes. As we can sort of guess from the graph over here, the person that scored a 3 in the blue class actually did a lot better than the person who scored 3 in the yellow class or the red class because their z-score is higher. They were 3 standard deviations away from their mean. Whereas in the yellow class, this person that got a 3 was 2 standard deviations from their mean, and the person in the red class was 1 standard deviation from their mean. So even though, you know, these 3 students, one in each of these classes, all got 3s, compared to the context of their class, they actually did differently, maybe under different circumstances, I don't know. But this gives us a more apples to apples comparison of these values. Any questions about this? The concept of a z-score can be pretty abstract, but if you want a formal definition, it's literally number of standard deviations away from the mean. Cool. Questions? Okay, awesome. So we talked about this, and here more about z-score. So as I mentioned before, a z-score tells us how many standard deviations away from a mean a point would be in a standard normal distribution. So same as what I said before. And also z-scores can be associated with cumulative probabilities. So as I mentioned before, calculating like the probability under a curve, the PDF, is a very, very complicated formula. So for any normal distribution, something else that's very helpful is that if we convert any value from any sort of normal distribution to the standard normal distribution, this z table just exists so that we can find out probabilities associated with that value. Earlier we ended up with z-scores of 1, 2, and 3. And we said that, okay, the probability of someone getting higher than that score in that particular class for the different curves, oops, I meant to draw a line. All right, for these different curves are going to be different in each of the classes. So therefore, I think we had a z-score of 1 for the red class, z-score of 2 for the blue class, 3 for the yellow class, I think. I forget. But anyways, different z-scores. And with these different z-scores, we can actually find out these different probabilities by using the z-table. So the z-table, by definition, shows you the probability of getting a score leading up to that score. So kind of the opposite of what we were talking about. We were talking about probability of someone doing better than 3. Here in this context would be the probability of someone doing worse than 3. So let's take a look at what the z-table is. If you just Google z-table, there are a bunch of different versions, but they all give you the same numbers. So the way that you use a z-table is you look up the z-score. And you can see here how it works is they let you look it up to 2 decimal places of your z-score. So for example, our z-scores that we got earlier were 1, 2, and 3. So just as an example of how to read this, let's say I wanted to find the associated probability with the z-score 1.64. So 1.64, I would actually look under 1.6 in terms of rows. So let me just annotate it so it's a little bit clearer. We're going to look at the 1.6 row and then the 0.04 column. So the probability associated with the z-score of 1.64 is 0.9495. So let's go back to our original z-scores that we had of 1, 2, and 3. For 1, we have a z-score of 0.8413. So that means there's a 0.84 chance that someone in that class did got a score of less than 3. Same for 2, you can see that the probability gets bigger for 0.9772 and in here 0.9987. So basically, as we move the z further and further out or greater and greater, the probability also gets greater. Another thing to see is that this z whatever the z-score is, again, we're moving it left to right down this line. And for this z, let me just draw it again. This mean is 0 and the standard deviation is 1. Again, good to always remember this. So therefore, if someone had a z-score of 0, you can see that the probability is exactly 0.5, just because if your z-score is 0, and remember how normal distributions are symmetric, the probability of being less than 0 is exactly 0.5. So this is just one way that you can translate any normal distributions, values, and probabilities into a standard normal distribution and then get their associated probabilities. That was not coherent English, but hopefully that made sense. That was my last slide. So any questions? Okay. We're going to talk more about this tomorrow.
Actually, I
think
had a
tomorrow.
quick question.
Oh, yeah.
With that chart, is it possible, is there like a function, like if we were doing this in Python, that would just automatically do this?
Yes, there is. Given any sort of mean standard deviation, there is a function somewhere. I think it's under SciPy or one called stats models. I forget which one is under. If you Google it, you'll definitely find it. Where you can give it a value, mean standard deviation. It will literally give you the z-score and also the associated probability.
Cool.
That's a good question. A lot of these things, there will be some formulas that turn up in the next couple, like this week and next week. Almost all of it is available, done for you in Python. Anything else? All right, the other things I wanted to mention is the z-score is different for when you're looking at a single point versus looking at a group of points. The only difference here is you have to divide the standard deviation by the square root of the number of points in like your little group. And we'll talk more about that, I think tomorrow, if not on next Tuesday. I think tomorrow we'll talk about it, but I forget which is in what topic. But yeah. To summarize, the most important things to take away from today are hopefully understanding what a z-score means for any normal distribution. Good to remember that the standard normal distribution is always a mean of 0 and a variance of 1. Perhaps just some things that like characterize a normal distribution. And then other important thing is just, I guess in a similar sense, a PDF, because the normal distribution is a PDF as well. How you can interpret a PDF and the fact that you can also associate the distribution of some of your data to be similar to a normal distribution. Those are some of the main things to take away from today. All right, any other questions? I will remember to throw that PDF up there. I also want to remind you all that if there's a lot of stuff in this phase, there is definitely a lot of stuff in this phase. A good place to make sure that you are at least ticking the boxes that you need to tick. It is in phase 5 because there's other questions in this doc, but in DS concept questions, as long as you're able to answer these questions, you should be good to go. This is, again, something that I've put together based on my interview experience, my other students' interview experiences. And from today, we should be able to be like, what is the probability density function? I do highly recommend thinking about how to answer this in your own words. Maybe take this doc, copy it, copy down the questions and write an answer somewhere, just so that when you're going back to study for interviews, you'll have an answer already. Another one that we can answer today, what defines a normal distribution and the standard normal distribution? So I guess let's reorder this just because we can. Okay, cool. Some of this other stuff we'll talk about tomorrow and also next week. So highly recommend this one. I've also linked the probability questions and the walkthrough that we had that I put on Slack yesterday. Cool. Any questions before we end off for the day? All right, if there are no further questions, I hope to see as many of you as possible in about an hour. I'm going to throw the link for our Hangout. I don't want to make it like a formal thing, but I'm basically going to be using Gather Round, which is the same thing that Dara used for orientation, just for us to try and get to know each other. I think it's going to be really important. So please make it if you can. It won't be awkward, I promise. But yeah, I'll throw the link into our Slack channel later on, but hope to see you, as many of you all there as possible. Okay, if there are no further questions, have a good rest of your day. I'll see y'all later. And yeah, as usual, anything y'all need, just feel free to Slack me. All right, have a good rest of your day, everybody. Bye.